Good morning. Okay, good morning. My name's Cathy Dunlop. I'm a researcher from the Institute of Marine Research here in Tromsø. And today we're going to learn more about how rapid changes in the Arctic is opening up new combinations of anthropogenic pressures to marine ecosystems, and how we can use that knowledge to adapt. For example, with much longer ice-free periods and changes in the climate here in the Arctic are opening up advances for enhanced human activities, such as increased shipping, seafloor trawling, extraction of resources, and even perhaps aquaculture. These new activities in previously untouched regions of the Arctic is leading to new multi-anthropogenic pressures on marine life, including plastic pollution, oil spills, noise, and impacts on the seafloor. So we're very pleased here today to welcome a group of international researchers working throughout the Arctic. That's including the Northwest Passage, the Canadian Arctic, the Barents Sea, Greenland, and here in northern Norway. I think I can say from behalf of all the session organisers, we were very impressed with the number of abstracts that we received, and we're looking forward to some very high quality talks today. So I think we're going to begin here with Griffin Hill from Nord University in Bøda in northern Norway. And Griffin is going to tell us about climate analogues and Arctic aquaculture.
Yes, thank you for that introduction. I'm Griffin Hill, a PhD student at Nord University in Bodø in northern Norway. And I'm here today to talk to you about Arctic aquaculture and the prospect of vulnerability even under a best case emission scenario. So I was lucky enough to stand on this stage last year and make kind of the simple argument that global approaches are required to address global problems. And I think we can agree that climate change is a problem that's acting on global scales. It's acting larger than individual measurement campaigns or transects can fully capture. And so we need tools and measuring sticks that match this scale. And I think that models are an important tool to fulfill this gap. And specifically, I'd like to talk about climate analogs and the climate dissimilarity models that produce them. This is one such global approach that can highlight areas or countries that are likely to experience the largest shifts due to climate change. So we know that climate change is happening in pretty much everywhere, but some areas are likely to be more affected than others. So what are climate analogs? And really, they're a tool to answer this type of question of how might a given place change in the future? And we can see that in action through existing tools, like from Copernicus. This is a terrestrial climate analog tool that where we can put in kind of whatever city we want, such as Tromsø, and say, what might it look like in the future, whether at mid-century or end of century under different climate change scenarios. And in this way, we can see that an analogous climate, which is what a tool like this is identifying, is the most similar climate at a given time and place for a set of defining environmental variables, so depending on how you define climate. We can use this to make bidirectional predictions, so we can ask and answer using the same tool what Tromsø might look like in the future, or where is Tromsø's current climate likely to be found. And one of the great strengths of this approach in relation to other modeling approaches is that we can do it without high-resolution occurrence data. We can project these things into areas or for species or taxa that do not have this really high-resolution occurrence data covering the whole globe. And I mentioned a bit that there's a defining set of environmental variables, and a lot of what goes into this is picking the right definition of climate for the job. For example, if we're interested in aquaculture, which is the point of this study, most aquaculture is still done in the ambient environment, so we'll include variables like temperature or salinity that can impact the outcome of that individual or species, but maybe we're excluding something like primary productivity because the species is being fed in the aquaculture context. And this specific approach is being used to construct climates and identify climate dissimilarity that is specific to aquaculture. And we're talking about aquaculture here in the context of the Arctic because while many don't think of the Arctic as a productive aquaculture region, it is. And 2% of global production and value of cultured fish and shellfish is produced here in the Arctic. And unsurprisingly, 93% of that is from Norway or northern Norway. But this 2% in the Arctic as a whole is more than the EU, which is quite surprising. So where I want to take this and where I kind of left off last year is that through this tool, through this estimate of climate dissimilarity using climate analogs, we can rank or identify the EEZs or countries that are most vulnerable under different climate change scenarios. And now I'm happy to present some of the results from that. And what these results look like, and kind of one of the ways we can present this is in the proportion of impacted aquaculture species within a given area. So these plots are showing via a heat map from green to red the proportion impacted in a given area, with red or 1 being all 100% of the species. And from the top, we have the Paris Agreement scenario, SSP 119, so limiting to 1.5 degrees of warming. And at the bottom, we have the most extreme scenario currently being considered, which is fossil fuel development. And then we have an intermediate scenario. And so the way that this was constructed was by modeling climate dissimilarity over the whole world and aggregating to a grid of 10-kilometer hexagons, and then generating per EEZ estimates of dissimilarity, which were calculated on a scale from 0 to 8. Don't ask me why 8 is the top of the scale. And then represented in terms of a proportion of aquaculture species impacted. And within this scale, greater than 0 is different. It's outside the range of the current species experience, so it's dissimilar from the entire range map of that species, and greater than 2 is a significant difference. And when we zoom into the Arctic, we can see that although there aren't huge areas that are impacted, the ones that are, a large proportion of the species is impacted, reflecting generally the relatively few species that are cultivated in the Arctic. And we can present this in another way by bringing in aquaculture productivity, or GDP. So here, in these next plots on the x-axis, we have the dissimilarity on the 0 to 8 scale per EEZ, and then on the y-axis, we have the aquaculture value in log $1,000 US. And we can break this into some kind of intuitive scenarios where if you have low investment and low vulnerability, maybe this is somewhere you want to be developing aquaculture. Whereas if you're on the other end of the spectrum with high dissimilarity and high investment, you're going to be in a mitigation stance. And then we have optimization and adaptation to kind of round those out. So starting from the most extreme scenario of fossil fuel development, in these plots, the named points are the top 10 in terms of dissimilarity. Don't worry about the shapes or colors for the purposes of this. The background points are the other countries that are significantly impacted, and the ones that are below 0 on the scale are NA values for the value of aquaculture. And so in this one of the most extreme, the main takeaway is no Arctic EEZs are among the top 10, and it's mostly low latitude and especially areas with enclosed seas. But as we move into same plot, but for the moderate climate change scenario, we can see that our first Arctic EEZ emerges with Norway being among the top 10 impacted. And you can see it's in this space of optimization. It's It's significantly impacted, but not hugely impacted, but has relatively high aquaculture investment. And when we go to the most mild and perhaps optimistic scenario, we see that the point cloud has largely vanished. There are a lot fewer EEZs that are impacted overall, but among those that are and those that are top impacted, we have the Arctic states emerging. And so what does this mean that these countries are kind of coming out in this mild scenario? And this is, I think, completely in line with what we've heard in other talks throughout the conference and in the literature, this idea of Arctic amplification and the Arctic being at the leading edge of climate change impacts. But that doesn't mean that there aren't opportunities for sustainable development or the continued growth of these industries. And as I said before, the exposure is driven largely by the current production of relatively few species. So I think that it's important to note that even under this most mild, increasingly unlikely climate change scenario, the Arctic and its aquaculture industry does remain vulnerable. But there's real opportunities to kind of protect what we have, mitigating existing operations, planning ahead to be aware of the change that's coming, while still preparing for what's next and identifying the future species or methods that are resilient in or even benefit from climate change in these areas. So with that, I'd like to thank my collaborators and co-authors on this project, which will hopefully be published very soon, and thank you all for listening.
Thank you, Griffin. And we'll hold any questions for the end of the session. So next, I'd like to invite Annika Heimrich from the University of Victoria. Annika is going to tell us about impacts of increased shipping noise on marine mammals and fish vocalization.
Yeah, thanks, Kathy, for the introduction. Good morning, everyone. Great to be here. My name is Annika Heimrich. I'm a PhD candidate at the University of Victoria in Canada, and I'm actually here today to present on a big collaborative effort between Transport Canada, the Department of Fisheries and Oceans Canada, the Wildlife Conservation Society of Canada, University of Victoria, and the people of Cambridge Bay in Nunavut. To provide a little bit background on the study site where we're working in, the community Cambridge Bay is located in the Northwest Passage on Victoria Island, and we heard it earlier already. We have rapid decreasing sea ice, especially also in that area, and a lengthening in the open water periods. So that means the community is experiencing more and more ship traffic coming through and cruise ships also docking at the community. And so there has been this massive collaborative effort started back in 2017, actually, trying to assess the underwater sound environment in that rapidly changing environment, especially with keeping in mind that that environment was historically very quiet and hasn't been exposed to all these kind of like anthropogenic factors. So we started deploying acoustic recorders back in 2017. You can see it a little bit further out around Finlayson Island, marked with that red star. That recorder is deployed a little bit deeper than the one at the blue star marking. We deployed between 2017 and 2019, had to stop, unfortunately, during COVID times, 2020, and then redeployed 2021 again. We also had a deployment out 2022. Unfortunately, that one was never recovered. And then the Hunters and Trappers organization also reached out and wanted to have a deployment a little bit closer to the community, maybe shedding some light also on the noise coming from community boats, essentially, and that one started last year, 2023. The objectives of that study are to, first of all, determine the acoustic presence of marine mammals and fish, many of which are important subsistence species for the Inuit. Second of all, then assess the ship traffic and ship noise in the area. And last but not least, be in constant exchange with the hunters and trappers and the elders of the community, hear about Inuit traditional knowledge, and also provide actually training about the equipment and the software to Inuit youth. tackling on the first objective, we are using a sound software that is known as Raven Pro. So it gives us the possibility to display an acoustic file more or less in a visual way. So you can kind of like scroll through the screen, find your detections, and that way a colleague of mine and myself have by now completed over 700 hours of manual analysis. So that's kind of like quite a stretch. We're not completely through yet. And we're finding 3+ species. And you can hear me saying 3+ species, because when you look at the Arctic cod, there's a question mark. And that means we're finding a lot of fish vocalizations, but unfortunately very little is known yet about fish vocalizations in general, and especially within the Arctic. So we're comparing it back to the literature, and we're guessing based on the shape and the sound and the frequencies that we're getting, it is Arctic cod, but the ground truthing is one big problem here, and we don't have the equipment yet to, for example, drop a camera for many hours and be lucky to record the fish exactly at the time when it's producing the sound to know which species it is. Yeah, talking about the ship noise, I mentioned earlier already, ship noise and ship traffic is ramping up in the area, and underwater noise has been recognized in many countries nowadays as a disturbance and also even harmful to the marine organisms. The area obviously has been historically been very quiet. So with the ship traffic comes the noise, and it can cause certain issues. First of all, it can cause what we call acoustic masting. So it means the noise coming from the ship, coming from either machineries or maybe propeller cavitation, can overlap the frequencies used by those species to communicate. So essentially it's limiting down the communication space. Behavioral changes have been reported, such as a flee response, for example, or a change in diving patterns, diving durations. These changes actually have been confirmed also by the Inuit. They've seen beluga whales, narwhals, and seals actually changing trajectory once the boat's coming in. Hearing impairment is an issue, and it could be temporal, it could be permanent, and last but not least, the physiological changes also have been reported in the literature, such as an increasing heart rate, for example, or stress hormone levels rising up. Yeah, to give you a little bit of a data preview here, what we found so far, you see these 3 bar plots here on the left-hand side. On the y-axis is the number in detections given, and turquoise stands for the ring seals, blue for the fish, pink for the bearded seals, and then there is actually a single beluga whale detection as well, 2017. We were lucky enough, the Inuit could confirm that sighting. We could hear it, they saw the beluga whale, and it's very extraordinary, because if you look at the location of Cambridge Bay, it's kind of like very deep in the Northwest Passage, not really the normal habitat for belugas to swim around there. So there's 2 options: either beluga came from the Beaufort Sea, or it actually came over from the high Arctic Baffin Bay population. And we will obviously try to follow up within the next years and see if we get more beluga vocalizations on our recorders. Nevertheless, what you can see, and I only displayed the shipping season, so August, September, and October, due to the time constraint of this talk, but we can see at least that fish seems to kind of like drop down a little bit towards October, raising the question for us, are these animals just quiet or actually maybe leaving the area? So that's a gap, a question mark that we don't know yet. And you can also see that we're missing actually some years here. Yeah? So we were a little bit unlucky. 2019, the recorder shut off before shipping season started. 2020, COVID hit and we couldn't deploy. And then 2021, we lost the recorder. So we're very excited. We just got the data back in hand from 2023 to actually get through that data and see what we're getting, with also the fact that 2023 was the year with the highest amount of cruise ships and pleasure crafts coming through the area. So that's going to be very interesting, and maybe have more to report next year on that. Yeah, talking about that circle very quickly here, these are all the vessel classes that we recorded within a 10 kilometers range and have been confirmed with AIS, and it has been already brought up many times also yesterday that there is still issues with AIS data, especially also in the Arctic, that we're hearing boats and we actually have no idea which ship it is. Yeah? So this is what we've at least could confirm so far. And then I want to focus your view quickly on that map here. So that was work based on Jackie Dawson's group. Back in 2018, 2019, they created this map with the community themselves, making a recommendation for a complete slowdown zone around the entire D Strait and Community Bay area. You can find it all in the Arctic Corridors and Northern Voices reports. And we're going to be updating this map now, based on the data that we're gathering and also interviews that have been actually conducted with the communities, mapping out key areas and potentially hoping to work towards more seasonal slowdown zones or maybe even no-go zones. So that's the next goal. Quickly for the community collaboration that we're working on, so all the results are always shared with the hunters and trappers up there. We're trying to be up in the community once a year and then follow up on a very frequent 2 to 3 month basis with online calls. We're providing training to the Inuit youth. I mentioned that earlier, so you can see me actually on the upper picture here. I was up there in August last year with 3 Inuit youth deploying equipment, training them on Raven Pro, trying to increase their knowledge on how to install any hydrophones, answer any questions. We got very unlucky with the wildfire season, I have to say. So out of a 5 days period that was planned to be out there, we managed to be 1.5 days on the water, and otherwise we were pretty smoked in and breathing wasn't so easy anymore. And otherwise I was mentioning earlier already that we have these interviews going on, so Oceans North is also involved in there. A part of the interviews have been already completed last year. There's going to be a report coming out, and there will be more interviews this year on mapping with Inuit knowledge and getting the entire community involved. And that brings me to my last slide. Lessons learned here. First of all, yes, we have some long-term data for the first time in that area, but we definitely need more to give proper management measures and bring up data that we obviously can rely on. Very crucial when you deploy any surface buoys in and around the community, make sure they're very visible, because if you have light colors, then people in that community get very excited that there's another beluga whale and they try to harvest your surface buoy. So that is not so helpful. Most times ring seals and fish are the species that we see right now exposed to the ship traffic, and both of them are absolute key subsistence species. And we see with a few vessel passings that we're missing them based on different recorder timings that we have. So we need to potentially adjust a little bit there to make sure we pass or get all the ship passings recorded in a very close approach. Last but not least, lack in AIS data. I think we all know about that. And if you want to model ship noise, you need bathymetry data. And that's still lacking, unfortunately, in the Arctic as well. And with this, I would like to thank you for your attention. I would like to thank all the people that are involved in that project, making it work, and especially a big thank to the people in Cambridge Bay who keep inviting us back on their lands. Kwana.
Thank you very much, Annika. And for the next speaker, we're going to stay with underwater shipping noise in the Canadian Arctic. So I'd like to welcome Deborah Sharp, also from the University of Victoria and the Wildlife Conservation Society in Canada.
Hi, everyone. Before we start talking about ring seal exposure to ship noise, I just wanted to point out we've added an author to our list here, Dr. Najim Shayahan. He's been incredibly helpful in developing the model, which I'm going to present. So with that, let's get started. As we've heard a lot about, Arctic vessel traffic is rising in the Arctic. Heard about that from the last talk. And with increases in vessel traffic, is increases in noise. That's especially problematic for marine species in the Arctic, where ambient underwater noise levels have historically been low. In the Arctic, we have 7 marine mammal species, and ring seals are the most abundant of these. They are important keystone species to food webs. They are important culturally to indigenous communities, and they are currently listed as a species of special concern in Canada. There's also rising concern, especially amongst northern communities, as to how increases in vessels and vessel noise may be impacting this important species. And while there have been a handful of studies seeking to understand the effects of anthropogenic noise on ring seals, none of these studies have focused on vessel noise specifically. But before we can understand what the behavioral or physiological impacts of noise may be to ring seals, we first need a better understanding of just how often ring seals and vessels actually co-occur in space and time. And to do that, we need data. Our ring seal data we used for this analysis comes from Department of Fisheries and Oceans Canada, which provided Argo satellite tracks in the Baffin Island area for 12 seals tagged in 2012, 2013, 2017, and 2018. And then we subset those tracks to just the fall months. And like many studies seeking to understand the effects of vessel noise, our vessel locations came from AIS data. But as we've touched on already, the problem with AIS data is that we know that not all vessel classes are mandated to use the AIS system. Our ring seal data was also a little imperfect, though, because it's Argos data. And Argos data is known to vary widely in quality and can sometimes contain a high degree of error. So we started by fitting our Argos data with a continuous time state-space movement model, which yielded fitted locations, which then we could use for our analysis. But in using a model to error correct our locations, we have to recognize that we end up with some uncertainty around each of these locations, which can kind of be visualized here with these 95% confidence ellipses. Now, they vary in size. Most of these ellipses, though, are at least 1 kilometer in diameter. That level of uncertainty could be acceptable in certain spatial analysis that are happening at kind of a coarse spatial scale. But in considering the effects of noise exposure on ring seals, we decided that we could not ignore this level of uncertainty and have tried to include it in our analysis. So that brings us to the important question. When we're thinking about ring seal exposure to vessels and vessel noise, what distance actually matters? We started by turning to the literature. And we found that Sweeney et al. Was able to estimate in an area near where we were working, where this data comes from, that ring seals could likely detect shipping traffic from 7.5 kilometers away. So with that number in mind and thinking about our confidence ellipses, we started by examining the number of occurrences where ring seals and vessels were within 10 kilometers of each other. And we found 28 instances. We then measured the distance between the interpolated vessel locations and the ring seal locations. And then we sought to describe exposure based on on the distance between the confidence ellipse and the vessel location itself. So if the entire confidence ellipse was outside the 7.5 kilometer range, we would consider that a non-exposure. Whereas if the entire confidence ellipse fell within the 7.5 kilometer range, that would definitely be an exposure. Now, we had likely exposures and potential exposures, but based on how much of that confidence ellipse fell within the designated range. And if the fitted seal itself was within the range, then we considered that the likely exposure. From the graph, you can see that we did have exposures and likely exposures in all 4 years of the study, with most occurring in 2013. Now, while these are intriguing results, we were really interested in what shipping vessels were responsible for these 28 seal vessel interactions. But we were surprised to find this list here. There's actually quite a diversity of vessels that were coming within proximity to the seals, which of course led us to believe that having this single detection radius of 7.5 kilometers doesn't make sense for all of these vessel types. So our current work is thus focused on creating this vessel-specific range of detection that can incorporate the vessel type and length, its speed at the moment, the bathymetry at its location, ring seal hearing sensitivity, and the seal-specific diving behavior in relation to this vessel. So how it works. We would start here with the basic tenet illustrated by the equation above, that the source level of a signal minus the propagation loss that happens as the signal moves through the water is equal to the received level of the signal at some distance away. While we do know the distance between the vessel and the seal, really what we're looking for is the range of detection at which the seal can detect or begin detecting that signal. And so for that, we're going to rearrange our equation so that now we can solve for propagation loss, which is is a function of range. Source level values can be calculated for a specific frequency of interest using the Joma-Pons echo model, in which the inputs are vessel type, vessel length, and vessel speed. And then next we need an understanding of ambient sound level at the time of each seal vessel encounter. And because wind is the primary driver of ambient sound levels during the open water period, we can approximate ambient using wind speed data and the Reader wind model. We can then combine this value with what is known about ring seal hearing sensitivity to calculate a detection threshold for a specific frequency of interest, which tells us how loud the signal has to be detected by the seal. So in our case, detection threshold is received level of interest. So our equation actually now looks like this. So we can now do the math, and we can solve for a propagation loss, and then use a semi-coherent propagation loss model, which incorporates both the bathymetry and the depth of the seal to then determine the range at which detection begins. Now, the methodology presented here is a very realistic way of modeling the range at which vessel noise becomes audible to a seal, and is something that can be applied to other species. I want to point out, though, that it does not describe the distances at which behavior or physiological impacts could occur, but it does provide a way to quantify how often vessels and seals are actually co-occurring in time and space, and then gives us the needed context we need for any future impact studies. This methodology also does not require low era location data, which is great because it means older Argos data sets can be suited to this analysis and may yield insight into past exposure rates, which can then be useful for making future comparisons. And lastly, our preliminary results indicated that 5 of the 9 seal vessel encounters that were deemed exposures were actually attributed to fishing and recreational vessels. And we know that these classes are underrepresented in AIS data, but yet were overrepresented here in our results, which further underscores, once again, that AIS data alone are not sufficient for evaluating the full scope of noise experienced by marine species. And with that, I'd like to acknowledge that this work represents a collaboration between Fisheries and Oceans Canada and WCS Canada. And I'd like to thank University of Victoria and the MITEX Fellowship Program for support during my PhD. Special thanks to Najim Shayahan, Ian Johnson, and Peter Thompson for helping write code, and to Annika Heinrich for helping conceptualize our exposure paradigm. And with that, I've included my email address. If you can't catch me in the halls, but you have questions or better yet, suggestions, or maybe your own Argos data, please don't hesitate to reach out. I'd love to hear from you. Thank you.
Thank you, Deborah. And please hold on to any questions for the end of the session. So now we'd like to invite Halvard Ström to the stage. And Halvard is going to tell us about the SeaTrack project, which is assessing the distribution of seabirds in the North Atlantic and overlaps with human activities.
Thank you. Yeah, I will talk about large-scale tracking of seabirds in the North Atlantic. First, acknowledge my co-authors from the Norwegian Polar Institute and the Norwegian Institute for Nature Research in Norway. Seabirds have a conservative life strategy. They lay 1 or very few eggs. They have delayed maturity, so the young birds do not start to breed before an age of 5, 6, 7 years old. At the same time, they are long-lived. These puffins can easily become 40 years old, and Seabirds are colony breeders, and when they have found a place to breed, they will usually stick to that for the rest of their life, and also together with their partner, usually. In the breeding season, seabirds are restricted to their breeding colony because they will have to raise their chick and protect the chick. But in the non-breeding season, which constitutes most of the year, seabirds migrate over huge areas or move over huge areas, and these movements are important to have knowledge about because human activity in marine areas have, or seabirds are vulnerable for human activity in marine areas. And the conservation status for Arctic seabirds is kind of critical. Just an example from the Norwegian red list, where more than 60% of the species are red listed, and the numbers are increasing for each revision of the list. And on the global scale, seabirds are the most threatened group of all birds. So the main goal with SeaTrack is to map the non-breeding distribution of seabirds breeding in colonies encircling the North Atlantic, and to try to understand how winter distribution affect demography and population development. In the map here you can see the colonies where we have deployed loggers. SeaTrack has a science component driven by a science plan and scientific publications, but also some clear management deliverables. We started in 2014 and are now into phase 3, which will last to 2026. To track these movements, we use GLS loggers. That's a small archival tag that we put on a leg ring. It measures light, and by measuring daylight length and the mid-time for dawn and dusk, we get a position per day. The downside of this technology is that the accuracy is not that good. So it fits best for these large-scale studies. And as it are dependent on light and the difference between day and night, we will not get data in equinox and during polar day and polar night. We have deployed loggers on 15 species, representing the 4 main groups of seabirds in the Arctic. And SeaTrack is a huge international collaboration. It involves scientists from 15 countries, more than 70 scientists, and a lot of field assistants that are deploying loggers, retrieving loggers, and collecting this data set. And so far, we have deployed roughly 70,000 loggers since 2014. We have retrieved roughly half of them. And you can see the database here with roughly 6 million positions, and it's covering all of the North Atlantic. And then what can we do with this data set? The first thing we do is to develop these kernel maps or heat maps that shows the expected distribution for one species, one colony. This is an example for common guillemots at Isle of May in Scotland. And we get this distribution core area. And we can do that for 4 different seasons in the year. But you can also then combine this for different colonies. This is an example with British guillemot or thick-billed murre. The colonies that are included here in this map are shown with black dots. You can see the metadata on the left side here. And these data and this data set and these maps are available online. So you can go into this address and look at the distribution and also combine all these different maps. And it's already widely used. We have taken this further in a new type of data set. In a three-step process, we are using movement modeling to try to fill the gaps that we get in the GLS data. We use distribution models to produce habitat maps, and then we merge this with population data. And then you get a new type of data or a new types of map, abundance maps, or population distribution maps, as we call it. We have developed this for 6 species, And the map here now shows the best available distribution map based on tracking, but combined with modeling for the colonies where we have not done modeling or tracking, sorry. And the unique thing with this map is that in each pixel you can go in and see what are the species that occur in that area at what time of the year, and also the numbers that you would expect to find. And this has huge management implications, or can be used for a variety of tasks. One of them, or one example here, is with offshore wind. Norway has decided to develop the Southern Nordsjøen II. And you might expect that the birds using this area are Norwegian, but they are not. The figure here shows that most of the birds during the year actually come from Scottish colonies. You can see the numbers and where the birds are coming from. So the development in the North Sea kind of influenced populations as far east as Novaya Zemlya in the Russian sector of the Barents Sea. You can see here where they are recruited from. And this also opens up a new era for looking at how winter distribution and how the environmental conditions during winter influence population development. This is an example with little auks, 4 colonies in Svalbard and Franz Josef Land in the Russian Arctic. You see the wintering areas here, and you see a hotspot northeast of Iceland. And by using this data set, we can look into how the environmental conditions in the wintering areas are affecting the populations. And we can also look into climate effects and also how weather affects seabirds. This is an example of wind patterns and how it helps or contribute to form migration corridors for kittiwakes with a kind of a highway going from Barents Sea and the Greenland Sea along the east coast of Greenland into the main wintering area, which is outside Newfoundland, and where you have a highway back into the breeding colonies during spring. So that's just 2 examples. And there will be a talk later today by Arnaud Tarot, who will show more on how these data sets can be used in different directions. So by that, I would like to thank all the founders and partners.
Thank you very much, Halvard. So now we're going to continue our journey in the marine ecosystem, and now we're moving to the seafloor, where we'd like to invite Monika Moric from the Environmental Defense Fund. We'd like to thank you for traveling here from California to tell us about how increases in bottom trawling because of opening up areas of ice retreat will affect the release of sediment carbon. Thank you.
Hi, everyone. I'm Monika Moric, and I'll be discussing bottom trawling. So climate-driven changes in the Arctic environment are setting up these potential challenges for fisheries management. Fish stocks are moving poleward to track thermal shifts, and ice melting is opening up access to more areas of the water and the seabed. And this is setting up potential for fishing activity to create climate feedbacks. And one of these is through the release of sedimentary carbon. There's also this increased interest recently in in Arctic blue carbon, or the carbon associated with marine environments, as a resource and a critical component of regulating Earth's climate. And there have been recently a few high-profile studies looking into fishing activity and sedimentary carbon release on a global scale. We wanted to take a more focused geographical approach here for the Arctic. So this method of fishing has a way of uniquely contributing to climate change. These large nets are rigged up and they scrape along the seafloor to pull up benthic species. And in addition to being a large source of disturbance for the benthic ecosystem, it also brings up a lot of sediment and the carbon within it. And a portion of that sediment reacts with the seawater, and it can become carbon dioxide as a gas that can go up to the surface and enter the atmosphere. So we wanted to identify key areas where this could be a particularly large release of carbon, and this can inform strategies such as targeted avoidance of particularly high carbon release areas. Now, trawling happens throughout the world, and it has for a long time, but it has been minimal in the Arctic so far because sea ice has blocked passage of ships, and this is beginning to change. So we wanted to know how much carbon could be remineralized by benthic trawling, and to give a broad overview, we combined projections of sea ice retreat, trawler activity, depth sediment carbon, and carbon remineralization potential. So we modeled what could happen from 2030 to 2100, and just to be clear, this is not happening yet, but we looked at two different climate scenarios. One was shared socioeconomic pathway to 4.5, in which emissions decline after 2050, and the more aggressive climate scenario of SSP 5, 8.5, in which emissions triple by the end of the century. We considered sea ice below 15% cover to be ice-free or operationally enough to allow ship passage, and then we considered 90 days of this condition to be sufficient for fishing to occur. So for our projections of future trawling activity, we used an existing model based on AIS data, and then it was correlated with temperature, bathymetry features, and sea ice concentrations, and we were able to convert this into hours. And then we were able to swap out future temperature and sea ice projections to get an idea of what trawling could be for these future decades. Our study area roughly followed the 50-degree north latitudinal parallel. However, there was some deviation from this based on data availability, and that is outlined in black in this map. Next, we calculated sediment remineralization, and so we used sediment carbon stock maps and combined this with our trawling hour projections, and we found the volume of sediment disturbed per hour of trawling activity based on commonly used ship speeds and gear type widths. Each decade, we adjusted the areas of projected trawling corresponding to the conditions of the climate scenarios we were using. And then finally, we calculated the percent of carbon that got remineralized that actually makes it to the surface as CO2, and this largely tracks with depth, although local currents definitely play a role. So this was the percentage of carbon that gets stirred up by trawling, and that does not go back to the bottom. Now there is a percentage of trawling carbon that gets stirred up that goes elsewhere, and we didn't track it, but it was not entering the atmosphere. And then to measure uncertainty, we looked at high and low estimates of trawling effort and aggressiveness of ice melt. We assumed that 100% of the carbon reaching the Earth's surface would enter the atmosphere. We assumed that liability or reactivity of that carbon was constant, as were decomposition rate and new sediment influx rates, and that trawling activity in sea ice area would be consistent for 1 decade at a time. And so here's what that looks like. We mapped where carbon releases were the largest, which were the Sea of Okhotsk, Bering Sea, Gulf of Alaska, Barents Sea, and the southern Greenland shelf. And in these maps, the areas in the warm colors represent more carbon release than the areas of the cool colors. On a per area basis, the most intensely trawled sediments were releasing up to 600 tons of organic carbon per square kilometer, and this is cumulative over 70 years. But most of the sediment that got trawled released less than 50 tons of carbon per square kilometer. Next, focusing in on the areas of ice melt exclusively, These were focused in on the fringes of the central Arctic Ocean, Greenland, and northern Canada. Carbon release in these areas was generally less than 50 tons per square kilometer. And so when we added up our entire study area's carbon release over the whole modeling period, this is what it looked like. In this graph, the year is on the bottom, and then cumulative carbon release is on the vertical axis. There's millions of tons organic carbon on one side, gigatons of CO2 on the other. Pick your preferred unit. And what we saw is that there was this general gradual increase. There were no major jumps up after any particular decade. By 2050, we saw 0.2 to 0.3 gigatons of carbon dioxide released. And then by 2100, that went up to about 1 gigaton of carbon dioxide. Now, on an annual basis, especially when you look at carbon per square kilometer, that might not be so much per year, but it really does start to add up over these longer time periods. Now, uncertainty is a little bit high. It was about a quarter of the mean, and there's work to be done in focusing our estimates. Next, looking at just those areas of trawling under melting ice, we saw that the two climate scenarios were pretty much the same until about 2070, and then they really started to diverge. And this is when they start to diverge in terms of ice coverage the most, and so that made sense. By 2050, remineralization of carbon was about 1 megaton or 1 million tons of CO2, and by 2100, that went up to 2 to 3 megatons. Our uncertainty for this was a lot lower. It was about 10% of the mean, or about 1/3 of a megaton. And one reason for this could be is that just the time for cumulative effects with ice melting later in the century is just a lot lower for propagating that error. So to put this into context, a gigaton of carbon dioxide is about 1/10 of global emissions from 2021. And there's still significant knowledge gaps that could be filled around carbon biogeochemistry and what's happening in the water column before the carbon gets up to the surface. We also want to know what happens to this non-remineralized carbon that still gets disturbed. Where does it go? Does it stay in the water column? Does it just settle back down? We don't know. And so this feeds into the bigger picture of managing Arctic blue carbon as a resource in a changing climate. And our activities to pursue one resource, fish, are impacting this other resource, which is blue carbon. And so I hope that this will be the start of a larger conversation on creating climate-informed fisheries management practices as we plan for the future of the Arctic. Thank you.
Okay, thank you, Monica. And next we have Geir Skea from Aquaplan Niva. And Geir will be online to tell us about simulations of large-scale oil spills on commercial fish species.
Thank you. Hope that you can now see my screen. So, Symbiosis was initiated to answer the following question. There was quite a high focus on the effect of oil spills and the Lofoten Vesterålen area, especially what would be the effect on the standing stock of the Northeast Arctic cod. So that started out the project with the first phase being a model framework and testing, and then a second phase where we did a number of case studies on Northeast Arctic cod. And now the third phase, which has been going on from 2018, where we extended the geographical area refined the toxicity algorithms, and we wanted to address multiple species and traits. Also to address multiple years, to look at the effect on years with good and bad recruitment on the stocks, and also multiple locations. Throughout these phases, the project has been led by Aquaplan Niva and with the Institute of Marine Research, SINTEF Ocean, and the Arctic University of Tromsø as key players. And in addition to that, there has been several national and international research institutes involved along the way. Symbiosis is a framework that links a number of different models, creating what we can see here in hydrodynamics and atmosphere, where we have a sort of a digital ocean with the current directions in 3 dimensions. Into this ocean, we have spawning fields of different species where eggs is released. And then these eggs turns into fish larvae, and these larvae graze on plankton and grows throughout the simulation. Into the same ocean, we also introduce oil, and wherever there is an overlap between oil and fish larvae and eggs, then an ecotoxicology model calculates what the effect on fish larvae and plankton is. This will cause a reduction in recruitment, and this reduction goes into the model to calculate what is the effect on a reduced recruitment in any given year on the fishable population or the spawning stock biomass. To address the potential variation in effects, we use 4 different sensitivity factors, the 2 of which, P1 and P2, use dynamic exposure, while the 2 most strictest assume an instantaneous mortality of any fish egg or larvae that encounter waters with more than 1 and 0.1 ppb PAH. So in this phase 3, we, in addition to cod, we also addressed haddock, saithe, herring, and capelin. We used 8 years of varying recruitment strength. We addressed the 4 toxicity parameter sets as we saw previously, and we addressed these in 24 different release scenarios, resulting in quite an extensive data set. Simulation set 1 is based on fields in planning or production, as well as exploration wells in open area on the Norwegian continental shelf. We use the information that forms the basis for permits in relation to oil spill response. So we looked at 9 locations from the southern North Sea and up to the Barents Sea south, with different oil types and quite a range in the release rates as well as duration. These are the results. See that for the 2 initial sensitivities, we cannot predict any effect in terms of mortality. And if you look at the 2 most strict sensitivities, we have a mortality that range from 0 to 2.5 and 8.8% respectively. The reason why we see no impact also for the most strict sensitivities is that will be scenarios where there is no overlap between oil and the fish eggs and larvae. This mortality, in turn, cause a biomass reduction, which is shown here. So assuming that we use the 2 strictest sensitivity factors, we have a reduction in a spawning stock biomass in a year at a maximum at about 2%. The second set of simulations used the same location that has been used in the previous phases of symbiosis, but we now wanted to look at what is the effect in terms of location in relation to the major spawning fields of the different species. So we use the similar input in terms of a release rate and duration for each of these locations. And the results show that we have now significantly higher maximum mortality of a year class, ranging up to 34%, applying the next most sensitive factor, and roughly 56% is a maximum impact for using the most conservative sensitivity. This in turn leads to a reduction in the spawning stock biomass, which is at the maximum of 18%, then in this term, in 9 years after the release. We can also see the effect of what is the original recruitment, which is the recruitment without any oil. And we can see that adding an added mortality will have very different results depending on the recruitment status for natural conditions, as shown here for 5 different years. So to summarize the results, if you look at the scenarios for existing or planned activities, we have a maximum mortality of fish eggs and larvae of roughly 9%, resulting in a 2% reduction in standing stock biomass or the fishable stock. While we for simulation set 2, which is in areas that's currently not opened and near major spawning fields, we see maximum mortalities of early life stages, roughly about 56%, resulting in an 18% reduction in the standing stock biomass. So with symbiosis, we can now simulate the impacts of an oil spill on future development of fish stocks. We can do that within the geographical area shown on the right side. We can also show how we can mitigate these effects, and we can also address the sensitivity in terms of years with different recruitment success under natural conditions. We can compare impacts from oil spill of different size, type, and location, and we can also identify areas of high potential impacts that will form important input to management plans. We can also use symbiosis to identify and give advice on data requirements for other species in terms of distribution of the population as well as the sensitivity. The symbiosis model framework is maintained by the research partners so that we can allow new simulations, including risk-reducing measures, and we are also looking into potential further development, looking at also other impact factors than oil pollution. So I would like to thank you for your attention. You will find the full final report from phase 3 of symbiosis, as well as links to the publications resulting from previous phases at the symbiosis website, which is given here. Thank you.
Thank you, Geir. And now we're going to move on to presentation from Katrin Vorkamp from Aarhus University in Denmark. Katrin will talk to us about chemicals of emerging concern in the Arctic and how these can be tracked, and also assessing risk to marine ecosystems.
Thank you for the introduction. And I would also like to thank the organizers for giving me the opportunity to present our work here today. So my presentation will be about organic contaminants in the marine environment of the Arctic, and the question where these contaminants come from. So local sources or long-range transport from lower latitudes. First of all, I would like to acknowledge my project team at Aarhus University, and of course our funding source, the Danish Environmental Protection Agency. We have monitored contaminants in the Arctic for many years. What you can see here on the slides, that PCB concentrations in ring seals from East Greenland. PCBs were banned in most industrial countries in the 1970s and 1980s, and then globally through the Stockholm Convention on Persistent Organic Pollutants in 2004. So, as expected, we see a decrease of these concentrations over time. It is generally established in the literature that the main source of these contaminants is the long-range transport from lower latitudes. So PCBs and other semi-volatile organic compounds can be volatilized, they deposit, they can be revolatilized, and in this series of hubs, they eventually reach the Arctic environment. So that's what we call the grasshopper effect. But we also know that there can be local sources of some contaminants in the Arctic. So these are data we published 20 years ago already, and they show various contaminants in short-horn sculpin at 3 locations in Greenland. So there's a location with no inhabitants, and then one with 40 inhabitants, and one with over 3,000 inhabitants. And you can see that many of the bars have equal heights, more or less. So that's mainly the organochlorine pesticides, which were not used locally, so they enter this environment from long-range transport. But 2 bars stand out with higher concentrations at the location with most people, and that's PCBs, and that's also PBDEs, which are brominated flame retardants. So apparently, the use in the Arctic of flame retardants in consumer products can lead to local emissions. And these local sources might be particularly important for current use chemicals in consumer and industrial products. So in this study, we picked 6 different flame retardants, 3 brominated ones, and then 3 phosphorus flame retardants, which are different from the brominated ones in their physical chemical properties. And we also included Dechlorane Plus, which is a chlorinated flame retardant, and that was recently added to the Stockholm Convention. And we conducted a modeling study, so no measurements except for comparisons with published data at Nuuk in Greenland. And I should mention that all these compounds have been found in the Arctic. We started with an extensive data compilation. And well, it was mainly the effort that was extensive, not so much the data really, because there's really not much information about production amounts or emission factors or other important data on these compounds. Nonetheless, based on the sparse data we had, we established emission inventories for these compounds for the Northern Hemisphere and then locally for Nuuk. We modeled the long-range transport using the Danish DEEM model, and we modeled the local emissions at Nuuk. And finally, we compared the model results to previously published measured data, although we did not have any from Nuuk, so there were other locations in the Arctic. And we compared the local versus the long-range transport. We also performed a small risk screening. And in the figure here, you can see the local model at Nuuk, which consisted of emissions to air, indoor and outdoor, emissions to soil, to the water, and also a mini food chain consisting of fish and seals. So a large part of the project were these emission inventories, where we considered the production of chemicals, the production of articles where these chemicals were used, the use of articles, and then the waste disposal. So all these steps can lead to emissions of the flame retardants. As I said, it was very difficult to find any information, reliable information, updated information, so we had to include many assumptions in this work. In this other figure, you can see what we came up with in terms of emissions from production sites. So a lot of production is taking place in China. The hexabromobenzene is also produced in Japan. For Dechlorine Plus, there was a major production site in the US, while now it is banned. So it's, as I said, difficult to find up-to-date information. Regarding the products, we considered the use of flame retardants in plastics, electric and electronic equipment, and textiles. And these results are shown in the lower figure, again, for different regions of the world. For this, we considered information about flame retardant use in different parts of the world and human consumption in terms of products that contain flame retardants. So this is the summary of the results. For each of the flame retardants, there are 4 bars. They show 2 of them are for local emissions, 2 of them are for long-range transport, and we have 2 because we have a high and a low emission scenario. These reflect the range of emission factors that we came up with. So the upper figure is air in picogram per cubic meter, and the lower figure is seawater in nanogram per cubic meter. And in all cases, you can see that the local emissions or the locally emitted chemicals led to higher concentrations than the long-range transport, slightly different maybe for the hexabromobenzene here. And the same is summarized in the table. So L is for local, and that usually exceeds the long-range transport. This question of local and sources and long-range transport is currently addressed in depth in an AMAP assessment. I have the privilege of co-leading the POP expert group under AMAP, together with the colleagues that are mentioned here. And in this work, we look in more detail at persistent organic pollutants, chemicals of emerging Arctic concern, and this question of local sources versus long-range transport. And this has policy implications. I have mentioned the Stockholm Convention before, and the Stockholm Convention has these 4 screening criteria, and one of them is long-range transport. And in that context, Arctic data have played a major role. But we've always anticipated that Arctic data reflect long-range transport. And we have to be more careful there because there can also be local emissions in the Arctic. So the key points I want to make are these. Local sources of current use flame retardants were relevant for Nuuk. However, and that's what a lot of Greenland colleagues have pointed out, Nuuk might not be representative of the Arctic as it is larger than most Arctic communities. Then secondly, increasing human activity in the Arctic might also increase contaminant pressure on the marine environment and elsewhere. And this might increase the need for technical and regulatory solutions. And finally, I did not show this, but this is a result of a previous AMAP assessment. Climate change leads to a remobilization and redistribution of previously emitted contaminants. So although most of these are transported from elsewhere to the Arctic, this can create local pulses to the marine environment. Thank you for your attention.
Thank you very much. And finally, we'd like to invite Ina-Helena Almqvist from Sintef Ocean to talk about plastic pollution in the Arctic.
Hello, everyone. I'm Ina-Helena Almqvist, and I work as a researcher at Sintef Ocean. And today I will tell you a little bit about adaptive ecosystem management in the Arctic. Seriously, plastic pollution is not a game, but in this study, we play it as if it were. So we chose to use a serious games methodology that combined learning and engagement in order to enhance understanding and governance of Arctic marine plastic pollution. So the Arctic is subject to the critical threat from marine plastic pollution. And this is impacting wildlife, human health, and our planet as a whole. So there's a no-brainer that we need to act. And at the global level, you have the UN Treaty to end plastic pollution that is being negotiated. But nations need to prepare for its implementation. And in our region, this depends on having effective Arctic governance. And this in turn hinges on having informed decision makers and scientists and people alike. And this is where I see my role as a scientist, that I have a responsibility to make learning tools such as serious games to ensure successful knowledge dissemination so that we can have more informed policymakers. For those of you not familiar with a serious game, it is a game that has a purpose beyond pure entertainment. And in our game that we developed together with the House of Knowledge, as a part of the two projects Gumplar and Plasticine, the players navigate governance challenges. They take on the shoes as a national government of a fictional country called Artesia. And here they are exposed to the impacts of plastic pollution from the 1960s and into the future. And the game that we had has a sustainability perspective. So at the beginning and the end, these 4 sustainable development goals are presented to the players, and they are asked to rank these in a prioritized order from their perspective based on what is most important for addressing marine plastic pollution. And after they've done this at the beginning, they're exposed to a series of events, and as a group, they have to agree on which specific mitigation efforts that they will take to manage these happenings. And to further succeed in learning and reflection, the participants that played this game about the Arctic marine plastic pollution, they have to evaluate the consequences, each event and each action in accordance with the triple bottom line. That is, how does this affect the environment, the society, and the economy, and quantify this on a scale from -3 to +3. And the serious games method is a way of taking some of these complex topics, such as that of Arctic marine plastic pollution, and turn it into something comprehensible. You separate it into smaller parts, and you make it into something that someone can relate to. So what we then saw was, okay, we have this cool game. This is nice, like we're researchers, but we need to put this into action. So we brought this game with us to the Arctic Circle Assembly 2023 and had a serious game session. And for this session, we had 67 participants, and they represented policymakers, business representatives, scientists, and students, to mention some. And they engaged and took on the role as the national government of this fictional country of Artesia. And we started first with a 10-minute introduction. Just what's the topic, what's the method? Then we have 45 minutes of gameplay. And then we had a joint discussion. And you can see our setup here with the different round tables and also the illustrative picture of our game board. So what we found from this decision-making was that when it came to ranking the Sustainable Development Goals, the participants chose to, in most cases, prioritize goal number 12 or 14 as their highest, with a slight preference for number 14, that's the below water. But at the same time, throughout the game, they said that industry and innovation were essential in order to combat this plastic pollution. So, and when it came to the efforts that they chose to take, we saw that some of the groups prioritized specifically for the environment, some chose to take action specifically for the society, and some chose to prioritize the economy. And when we looked at their arguments for choosing this different, either for the prioritization of the Sustainable Development Goals or for which action that they saw fit most for this specific event, They related this to their experiences and their knowledge. And this is what is key when it comes to governance of Arctic marine plastic pollution and Arctic governance in general. Because when we see that, there's a connection between the knowledge that we have and the actions that we take, that means that if we are able to become more informed, we as a society can steer our decisions towards a more sustainable future. And based on at least the feedbacks that we got from a game such as this session, we saw that you're able to become more informed about a topic by engaging in a session such as a serious game. And personally, I believe that the clue here is to take this complexity, such as that of Arctic marine plastic pollution over time, and turn it into something comprehensible, separate it into parts, such as events that players are exposed to over time. And then to ensure the learning and reflection, you have to ask them to make a decision. And they have to stand by this and have ownership to this decision and see how the choice that they made had consequences over time. And then I think that you need a personal connection in order for this to be memorable. And then we had a storyline that throughout the game you follow this young girl called Glacie. And empowering sustainable choices by increasing the awareness of Arctic marine plastic pollution and governance thereof is key if we want to have a healthier planet and if we want to have a protection of our shared future. Here is an overview of the team that developed this game and the study that we carried out. If you want to have any discussions about topics for serious games or questions about marine Arctic plastic pollution, feel free to contact us. And hopefully maybe we can have some questions after too. Yes, thank you.
Can Helena, can you stay on the stage? And can I invite the other speakers to please come on the stage? Sorry, we only have 2 seats, so yeah. It's only 5 minutes. I'm sure some can stand. And then we're going to open up the floor for some questions. Do we have any questions? If you please just raise your hands and you'll receive a microphone. Okay, we have one.
Hello? Oh, it works, okay. Hi, my name is Lauren Decker. I'm with a company called Polarctic. I was interested in the resuspension of dredged materials, and I'm aware that the bottom material isn't particularly well documented, and I was just wondering how that impacts assessment of carbon being dredged up.
Can you hear me? Okay. Yeah, that's an interesting point that this could apply to dredge materials also. This is a fairly new topic, and there's a bit of debate about the biogeochemical processes at play, but I definitely think like depth is a big component of how much carbon could be released to the atmosphere. If you do it deeper, generally, the pressure from the water above is a force that helps keep that gas dissolved in the water. Now that varies with local water chemistry and currents and other processes. But I think largely if you do it in shallow water, you have a higher likelihood of having carbon be released from that process. Now, since dredged material, if it's dredged over and over, you reach some point of diminishing returns where all the carbon that could be released is. And so I think it really just depends on the conditions. I hope that answers your question.
Okay, thank you, Monica. Okay, do we have any more questions? Yes.
Yeah, my name is Harold Steen. I'm from the Norwegian Polar Institute. I wonder about the noise and the harbor seals. Can you say something about harmful levels, or you talked mostly about detection and you modeled interactions, but can you tell us a little bit more about how harmful do you think it is?
Thanks for that question about ring seals, right? No, basically we need more studies out there that can actually look, when we talk about impact for any species, whether it's whales or belugas or narwhals or ring seals, the level of impact varies. You know, we can say that there are probably ranges where physiological impacts may happen, where hearing loss could happen. There are probably ranges at which behavioral impacts may happen, where maybe cessation of foraging activities change. But the zones of all those different types of impacts have not been established for many species, but especially not for ring seals. And that was kind of what I touched on in terms of mentioning that there's really a lack of literature and studies addressing what all those potential different zones could be. So the model that we've presented is taking the coarses scale, which is just saying, before we can even address what some of those smaller zones of impact may be, we just need to understand where and what distance ring seals can even hear these vessels, because you would assume that there aren't going to be any behavioral or physiological impacts if the animal can't even detect the sound. So this was kind of just first step, and again, setting a context so that later on, other folks can try and ascertain what some of these behavioral and physiological impacts may be, and those would likely be at a much smaller scale with 1 or 2 animals. So you could broaden that out if you knew what the exposure rates for the species as a whole might be.
I have a question for Katrin about the chemical pollution, if I may. Thank you for a very interesting presentation. I was interested about the local sources. Is that primarily from waste incineration that the chemical pollution is generated? And if so, surely there's a policy change that could be made to prevent waste incineration in these communities?
The waste incineration takes place in many Arctic communities, probably know, and it's often difficult with alternatives, because there's no waste collection system and places are remote and people don't have any alternatives to get rid of the waste. But of course, that is a source. It can also be a source of these flame retardants that we work with, because they're plastics and then they get burned. But in this assessment that we're doing for IMAP we also identified other local sources, for example, with wastewater, which is often not treated in the Arctic, but also infrastructure, like airports, for example. And then it's a question if that can be considered a local source, but as I also touched upon in connection with climate change, the permafrost is thawing, for example, and releases a lot of contaminants. So all this together adds to these local impacts. And then the question is, how much does it matter beyond these local impacts? So that is something we're looking at too. But it's important then, as I said here, with regard to Stockholm Convention, that we distinguish between the local observations and then the long-range transport to remote areas. Yeah, but waste incineration is certainly one point that needs improvement.
Thank you.
We have time for one more question.
Hi. So I was really excited to see the Sea-Track bird maps, heat maps, and I was wondering if there was any goal to expand to other areas like Alaska.
Yeah, that's something we look into. We have been encouraged by CAF and this AMBI project to also start to look into the Pacific. So that's something we will look into through phase 3. We have already expanded quite a bit now, including East Canada and actually East US. So we have enough to do at the moment, but we will look into if there are potential for collaboration and expanding further. Yes, making it kind of a circumpolar.
Thank you. So I think that brings us to 12:30. So we'll have to wrap up the session there, but I'd like to say particularly a big thanks to all our speakers who've travelled here today to present such interesting array of results.